Hey everyone, and welcome back to another Explainer. Today, we're going to explore the invisible, totally vibrant architecture of the world around us. We're talking about the physical principles of sound. Now, sound is something we experience literally constantly, right? From the music blasting in your headphones to that distant, low rumble of thunder. But the actual physics of how that sound travels from a source right to your ears, it's absolutely fascinating. So let's just dive right in. To really wrap our heads around what sound is, we actually need to start by looking at where it isn't. You know all those epic sci-fi movies with the massive booming spaceship battles? Well, physically speaking, they are completely inaccurate. Which brings us to our opening question. Why is there absolutely no sound in space?
Think about a scuba diver underwater and someone just standing outside in the air. They can both hear a siren going off. But an astronaut floating in the vacuum of space, they'd hear absolutely nothing. Zero. And the reason for this is that sound waves are what physicists call longitudinal waves. They entirely depend on a medium, like air, water, or even solid bone, to vibrate and actually carry their energy forward. In the total vacuum of space, there simply aren't any molecules to vibrate. No medium means no sound. It really is that simple.
Okay, here's our roadmap for today. First, what is sound? Then, the sound spectrum, the anatomy of a wave, the speed of sound, and finally, how sound behaves. Section 1. What is sound? So technically speaking, sound is the mechanical oscillation of any medium traveling as kinetic energy produced from a vibrating source. Now, the really crucial part of that definition is the emphasis on kinetic energy. Unlike light, which is electromagnetic and can just happily zip right through the vacuum of space, sound is strictly mechanical. It's the literal, physical bumping of molecules against other molecules, transferring that kinetic energy in a big chain reaction. Imagine a tuning fork. When the prong pushes outward, it actually squishes the surrounding air molecules together. That creates this high pressure band called compression. But as the prong snaps back, it creates a low pressure void, pulling those molecules apart. We call that rarefaction. So the big takeaway here is that sound isn't just a single smooth line. It travels in alternating bands of compression and rarefaction, literally pulsing its way through the medium. Moving right along to section 2. The sound spectrum. When we look at all the frequencies of sound out there, it's a massive scale. You have incredibly low, slow waves on one end, going all the way up to incredibly fast, tight waves on the other. And as humans, we occupy just a tiny, specific band right in the middle. Way down on the low end, you've got massive creatures like whales communicating across entire oceans. And way up on the high end, way past the hearing of bats, we actually harness ultra-high frequencies for things like medical ultrasounds to see inside the human body. Let's put some hard numbers on this, just to put it into perspective. Normal human hearing ranges from 20 hertz, down at the absolute bottom, think the deep, thumping rumble of a bass guitar, up to about 20,000 hertz, which is like the piercing shriek of a dog whistle. Anything below 20 hertz is called the infrasonic range. We can't hear these, but we often feel them as vibrations right in our chest, like from a distant earthquake. And anything above 20,000 hertz is the ultrasonic range, which is totally dominated by animals like bats using echolocation to navigate in the dark. All right, section 3, anatomy of a wave.
Now, we've been throwing the word hertz around a lot, so let's quickly define it. Frequency is simply the number of complete oscillations a wave makes in exactly 1 second. It's usually denoted by a lowercase f and, you guessed it, measured in hertz. So if a wave oscillates 500 times in a single second, that's 500 hertz. And it's pretty simple. The faster the oscillation, the higher the pitch we hear. Now let's talk about amplitude. That is the vertical height from the resting centerline right up to the peak of the wave. Amplitude dictates loudness. And here's a totally wild quirk of physics for you. Loudness is directly proportional to the square of the amplitude. Right? So if you double the amplitude of a wave, you don't just double the volume, you actually get 4 times the loudness. Crazy, right? Now moving horizontally, we have wavelength. Represented by the Greek letter lambda, this is just the physical distance between 2 consecutive peaks, or compressions. We also have the time period, which is literally just the time it takes for one complete wave cycle to pass a specific point. It's basically 1 divided by the frequency. High frequency means a short time period and a short wavelength. They are intimately linked together.
That brings us to section 4, the speed of sound. In air at room temperature, sound travels at about 343 meters per second. Now, you might intuitively think that because water is thicker and denser than air, it would slow sound down, right? But actually, in water,
Sound travels at nearly 1,480 meters per second. And in incredibly dense solid steel, it skyrockets to almost 5,960 meters per second. No way, right? But it's true. Why? Because of elasticity. Even though steel is super dense, its molecules are so tightly bound and highly elastic that they snap back into place almost instantly, passing that kinetic energy along incredibly fast. So yeah, elasticity totally beats density when it comes to speed. This dynamic between density and speed leads us to a concept called acoustic impedance. Basically, you can think of this as a medium's natural resistance or opposition to sound flow. It's calculated by just multiplying the medium's density by the speed of sound within it. Another absolutely vital factor here is temperature. As a medium gets warmer, its molecules get more energetic, which means sound actually travels faster in warm air than it does in freezing cold air.
And finally, Section 5. How sound behaves.
The first major behavior we see is reflection. When sound waves strike a hard, flat barrier, they don't just stop dead, they bounce back within that exact same medium. And this perfectly explains the geometry of an echo. The angle that the sound hits the wall is the exact same angle it bounces off. This is precisely why shouting into a canyon or a big empty hall results in your own voice bouncing right back to your ears. But what if the environment itself changes? Well, that's called refraction. Remember how we just said sound travels faster in warm air? Okay, picture sound traveling over a cool lake. The air higher up is warmer, so the top part of the sound wave moves faster than the bottom part that's down in the cool air. This difference in speed literally causes the sound wave to bend downward toward the water. It's refraction at work, and it's exactly why you can hear people talking so clearly from all the way on the other side of a lake on a cool summer evening. Now, as sound travels, it obviously doesn't go on forever. It experiences something called attenuation, which is basically the gradual weakening of the wave's intensity. When sound hits soft insulation, for example, two things happen. First, scattering. The wave gets deflected into a million random directions. But second, and honestly most interestingly, absorption. The mechanical energy of the sound wave actually gets converted into a tiny, tiny amount of thermal energy, or heat, within the material. The sound literally exhausts itself as heat. Finally, we absolutely have to talk about one of the most famous wave behaviors in all of physics, the Doppler effect. This is the perceived change in frequency when the source of the sound and the person actually listening to it are moving relative to one another. We have all experienced this for sure. Imagine a car honking its horn while speeding directly toward you. Because the car is moving in the exact same direction it's emitting the sound, it's essentially chasing its own sound waves. This causes the waves at the front of the car to compress and bunch all up. And as we learned, a shorter wavelength means a higher frequency, which is exactly why the horn sounds like it has a much higher, more frantic pitch as it approaches you. But then, the exact opposite happens the second the car passes you. Now, the car is driving away from the sound waves traveling back towards you. The waves are literally being stretched out. A longer wavelength means a lower frequency, which is why the pitch of the horn suddenly drops to a deeper tone as the car speeds off into the distance. That classic meow sound of a passing race car? Yep, that is the Doppler effect in action. Which brings us to the end of our journey into the awesome physics of sound. Right now, as you're listening to this explainer, kinetic energy is causing the speakers to push air molecules, which are traveling at over 300 meters per second, bouncing off your walls, occasionally turning into microscopic heat, and ultimately vibrating right inside your ear. It's kind of mind-blowing to think about. So, I'll leave you with this. How are the invisible sound waves around you reflecting, refracting, and interacting right in this very moment? Once you understand the physical principles, you realize the world is just this massive symphony of moving energy. Keep observing, and I'll catch you in the next explainer.